Your phone, laptop, even your microwave are powered by logic gates. Believe it or not, these simple operations are what make watching YouTube videos even possible. In this video, you'll not only learn what a logic gate is, but how just 3 of them can be combined to create much more complex behavior. The kind of logic that powers everything from simple circuits to entire CPUs. Hey, I'm Oliver, a final year computer science student. When I first started off my studies, I struggled with some of the core concepts, but over time I've managed to break them down and truly understand them. In this video, I want to make one of those fundamental topics, logic gates, clear and simple for you, so your own journey in computer science can be a little smoother than mine was. So I'm going to start off with a little bit of side information. So as you can see here, we have 3 diagrams, and these are each considered logic gates. Now we're going to be concentrating on the NOT, OR, and the AND logic gates, but there are several more. However, these are sufficient for doing most computations. So what's important to notice here is that each of these diagrams has a left side and a right side line. The left-hand side line here is considered the input and the right-hand side one the output. You can see that there can be several inputs, and the same is true for outputs. However, these are more complex gates, which we'll not get into right now. The inner workings of a logic gate are composed of transistors. Transistors power most computers, but because they are a little more complicated to get into, I will skip over this in today's video. Another relevant concept are truth tables. These allow you to write the functionality of a logic gate in a clearly visible way. As these diagrams don't really tell you much about how they work, truth tables like these are supposed to make it easier. The way you would read one is you would have a column for the output and however many columns you need for the input. In our case, we have 2 inputs, A and B, and an output C. A row is one formula to follow. So, for example, if our input is A is 1 and B is 0, then what we write here in C, for example 0, would be the output. So when A is 1 and when B is 0, then C is 0. Now, this also means that we can't have another entry here that says the opposite. So we can't have the input 1, 0 equal 2 different outputs. Another relevant thing, which I skipped over, is that we only have 1s and 0s in our computer. So we only know when something is on and when something is off. For this reason, these gates are called logic gates. In logic, we have true and false. If you want to learn more about how computers deal with numbers, I suggest you check out my video on binary numbers. But now coming back to truth tables, I have filled out 1 entry here. However, there are a total of 4 different input combinations. For each input, we have 2 values, either 0 or 1. And since we have 2 inputs, we have 2 times 2 inputs. So that would be 2 to the power of 2. So if we had 3 inputs, for example, if there was a third one here, we would have 3. And we would write 2 to the power of 3 instead. So the number of different combinations you have is just 2 to the power of the number of inputs you have. So in this case, we have 2. Then you would fill out this table with all the different combinations. And once you have all the input combinations, you would fill out the outputs to define what the behavior of a gate is. To have this make a bit more sense, I'm going to start with the first logic gate so we can see it by an example. The first logic gate we'll be looking at is the NOT gate. The NOT gate simply inverses the input. If the input is 0, the output will be 1, and if the input is 1, the output will be 0. So now this truth table tells us what the functionality of this gate is. Moving on to the next gate, we have the OR gate. The OR gate is pretty easily explainable. It is always true if at least one of the inputs is true. This means that for the input A and B, so these 2 inputs here, both being 0, the output C will also be 0. Moving on, having B be equal to 1 means that at least one input is 1, and our output would be 1. The same is true for the inputs A being 1 and B being 0. We again get 1. And for the input of A is equal to 1 and B is equal to 1, our output is also 1, because at least one of the inputs is 1. Now coming to the last gate we look at, it is the AND gate. The AND gate is also quite straightforward. The output is 1 if both of the inputs are 1 as well. So in the case where both of our inputs are zeros, we will output 0. In the case, or both of these cases, where only one input is 1 and the other one is 0, we will output 0 as well. And only in the last case, where both inputs are 1, our output will be 1 as well. Now I'm going to show you some examples in the School Online tool. Here you can add input nodes as well as output nodes and the gates that you've learned. So we'll start off with a NOT gate, and we can connect these different nodes with one another. Here you see that the output turned yellow. This is because the NOT gate inverses the input, and currently the input says 0 since it's off. If we now turn it to 1 by turning it on, the NOT gate inverses the 1 and turns it into a 0 in the output. That's why it's not yellow any longer. We can also check out the other gates that we went over, like the AND gate. Here you see that if either input is on, but not both of them, there is no change in the output. It's still 0. And if we look in our truth table, this is the expected behavior, as only when both inputs are 1 do we want the output to be 1. And this is also the case. Now moving on to the OR gate. Here's the truth table one more time. Here you can see that the output is only 0 if both inputs are 0 and is 1 in any other case. So it's 1 if there's at least one input, A or B, that is 1. And here you can see it as well. Turning one input on turns the output on, turning the other input on also turns it on, and turning on both has the same effect. I will now show you one gate that we have not covered yet, but that we're able to replicate with the gates that we've learned. The gate that I want to show you is the XOR gate. XOR stands for exclusive OR. This means that it will only be true if exactly one input is true. So if we turn one input on, the output will turn on. If we turn only the other input on, the output will also turn on. However, if we try to turn on both inputs, the output will not be on. Here I have now added a couple more nodes to show you that the XOR gate can also be done using just AND, OR, and NOT. On the bottom, you can see that I used two AND gates, a NOT gate and an OR gate. And on top, you can see the XOR gate from before. I have connected them to the same inputs so that you can see that the top and bottom output will turn on and off at the same time. So if I turn one on, both are on. If I turn both on, neither will be on. If only the second one is on, the output will be on. And if none are on, it will be off again. So you can see the XOR gate can be made using just AND, ORs, and NOTs. There are also these other gates, however, all of them can be covered by just these three gates. And what is also very interesting is that there is one gate which allows to replicate all the other gates, so you don't even need the three gates, but that is perhaps for another video. If you found this video interesting, you might enjoy my other videos, for example on binary numbers. They'll give you a solid sense of how we use just zeros and ones to represent and store information in computers. And if there's a concept you've been stuck on, drop it in the comments. I'd love to help make it clearer. Thanks for watching.